Good afternoon, everyone. My name is Giovanni Giustini. I am a lecturer in engineering, simulation, and data science in Mace, the University of Manchester. Today, I'm wearing my hat as a CFD person. I would like to give you an overview of some of my research in boiling. And so I would like to show you some of the contributions that we have been able to make via applying fundamental CFD simulation to boiling problems. So a little bit of introduction. So first of all, why two-phase flow and why boiling, and what are the applications of boiling? Where do we find boiling? Okay, so a couple of obvious examples are from the energy sector, both nuclear fission and nuclear fusion. So most of the nuclear reactors currently operating in the world are water-cooled reactors, and in these kinds of reactors, water undergoes boiling, especially in the reactor core, even for reactor designs where there is no direct generation of vapor in the reactor core. In fusion, the application is not as obvious, but there are some components in tokamak-style plasma fusion reactors. There are some components that are basically exposed to the plasma. They need to withstand huge heat fluxes. And how do we get rid of this heat? Via circulating a boiling fluid, typically water again. Same problem in thermal management. For example, processor chips. These are extremely high heat flux components. And there is also a similar issue that needs to be overcome in battery technology. So people nowadays are beginning to experiment with boiling to cool battery packs. Finally, a somehow exotic application, in my view, something that isn't very relevant to the United Kingdom, and that is solar power, for obvious reasons, not so relevant to the UK. And so there are some concentrated power, there are some solar power concepts that exploit a boiling fluid as the heat transfer fluid. So in concentrated solar power receivers, sometimes there is boiling sodium. Now, the application I'm most interested in is actually the application of boiling to nuclear power, and in particular light water reactors. So in the core of these kinds of reactors, we have a two-phase mixture of liquid water and steam undergoing boiling. And the conventional approach used in industry to tackle these kinds of problems is basically to consider that we have a mix, say, of steam bubbles and of single-phase liquid in our fuel channels, but more generally, say, in a pipe. And we use a rather standard CFD approach to model this kind of problem that is based on the so-called Eulerian modeling approach with interpenetrating continua. So we are saying that everywhere in our simulation, there is a little bit of vapor and a little bit of liquid. These are treated basically as continuous phases, and we use a pretty standard steady state CFD simulation to compute various quantities of interest, such as, for example, the fraction of area in our pipe that is occupied by the vapor phase, that is normally called in the literature a void fraction, and other quantities of interest, such as, for example, how hot my wall becomes depending on the imposed heat flux or power generation at the wall, and depending on the various flow patterns that we are predicting, and so on. So nowadays, in two-phase boiling and nuclear research, one of the major challenges is to go beyond this large-scale, coarse-grained, if you like, Eulerian approach, and actually try and develop physically based modeling of the fine details of the flow using so-called interface resolving simulation. I'll get back to that in a second. So the idea is that, okay, we know that there is a lot of physics in boiling flows, especially near the solid surfaces where heat is applied. So we have very subtle and somehow exotic phenomena associated to the growth and departure of steam bubbles at the solid surface. And here we're talking about very small scale phenomena, 1 millimeter and smaller, and very short duration, a few milliseconds, hundredths of a second. and things like that. So very small scale and very short times. And the idea is to use physically based simulation to predict with great accuracy the behavior of the single bubbles or of small populations of bubbles, and from there gain an understanding of the actual physics of boiling flows. So, and obviously, on the one hand, this needs to be supported by macroscopic local measurements from for validation of the simulations. And on the other hand, a caveat, just want to make it clear that we are, in a way, unpacking the overall superset problem of predicting the whole of the bubbly flow in a pipe or in a nuclear fluid channel, and we are just looking at select aspect of the bigger problem. Really, nowadays the objective isn't really to simulate the whole of the bubbly flow in a pipe with all the myriads of bubbles growing. So that's really at a distance in the future. So right now we are content with just looking at one or a few bubbles, and from there make our conclusions that can be applicable to, say, more macroscopic descriptions of boiling flows. And so a little bit of a technical detail before I show a couple of examples from my research. Now, the simulation methodology that I've been using and that underpins some of the results that I'm going to show is so-called interface capturing CFD simulation. Now, what is it? It is basically a technique that works in tandem with ordinary CFD simulation methodologies. It's interface capturing is a technique that is used to model the transition region between two fluids, such as, for example, if you want to model bubble behavior, you have the curved surface of a bubble, and you have that the interfacial region is basically a very narrow and thin region separating the vapor and the liquid. Now, this is the representation of this interfacial region in the CFD domain. So we can see already that this is not what you usually do in CFD, because we basically have in our CFD simulation, we have a few cells where all the action is, and from the point of view of modeling the behavior of the interface elsewhere, cells are more or less idle. There is transport of heat and mass in the bulk phases, but still all the action is at the interface, which from a mathematical point of view, the interface is basically treated as a smoothed Heaviside step distribution, where an indicator function varies from, say, for example, 0 in one phase to 1 in the other phase. So we have that our liquid, the red, would be indicator function equal to 1, and the vapor, blue phase, would be indicator function equal to 0. And over a few cells, our indicator function varies from 1 to 0. Just to have an idea of what's the basic concept of interface capturing simulation. So what can we do with this? Couple of examples taken from research applied to boiling, and in particular for nuclear applications. So example number 1. Now, let me start with some observations from the laboratory of my colleague, Professor Hyundai Kim in Korea, Kyunghae University. These are observations of a single steam bubble growing at a solid surface in pool boiling conditions at low pressure, atmospheric pressure, actually. So the top row of images is a side view of the bubble with a camera. The middle row of images is an image from the underside with interferometric technique, which is suggestive of the presence of fringes typical of an interference pattern that may suggest to us that actually beneath the bubble, in between the bubble and the solid wall, there is actually something else. There may be a liquid film, and I'll come back to that in a second. And third row of images, these are infrared measurements of the temperature distribution at the solid surface beneath the bubble. Again, red is hot, yellow, green, and blue are progressively cold regions. So there seems to be a significant cooling effect. So what is going on here? Well, the thing is that there is beneath the bubble a very thin liquid film, say 5 microns in thickness and something like 1 millimeter in radial extension, that is originally formed as the bubble expands due to fluid reaction and viscous forces, but most importantly, it also eventually evaporates. So it generates a vapor that goes into inflating the bubble. So the presence of this layer can have a very important effect on bubble growth and therefore on boiling heat transfer, which depends crucially on how large are my bubbles at departure and therefore how much energy I remove from a surface via the latent heat transport associated to bubble formation. Right, so can we study this kind of physics with CFD? Well, the answer seems to be yes. So with interface capturing simulation, we can develop detailed high fidelity models of the hydrodynamics of the growth of a single bubble at the surface. And from these models, we can study the behavior of the liquid film beneath the bubble. Purely from a hydrodynamic point of view, we are artificially inflating the bubble. And as a consequence of its growth, there is the liquid film left behind beneath the bubble. And we can actually extract its profile versus time. And so it's radial variation of the liquid film thickness versus time and so on, and compare with measurements. So here in the two images, I am showing comparison with measurements from Professor Kim's lab, which seems to indicate that CFD with interface capturing is doing a pretty decent job at calculating the hydrodynamics of microlayer formation, and therefore what kind of values of the thickness of the microlayer we should expect to be left behind beneath the bubble in the early stages of bubble growth, and therefore potentially how much liquid can be generated from it later on when a bubble in the later stages of bubble growth. Now, these later stages of bubble growth actually are the subject of another contribution. So another contribution that I would like to summarize for you is what happens after these microlayers have disappeared. And so what happens when to the heat transfer around the bubble when a bubble is just about to depart and say a little bit of time after it has departed. This is the so-called quench heat transfer. Now, why I'm calling it quench? Okay, let's again have a look at these images. So we have the top row of images is a side view of the bubble as it grows on a surface, and the bottom, the two rows of images at the bottom are the phase distribution on the solid surface from simulation, and below it, the phase distribution of the solid surface from experiment. And again, from Professor Kim's lab. What happens after, say, at around 15, 16 milliseconds once the microlayer has disappeared? Well, what we have is that we have basically that in contact with the heated wall, we do actually have a dry patch. So we have that the solid is beneath the bubble is exposed to the vapor phase. And we have that this dry patch beneath the bubble is shrinking with time. Therefore, we have an advancing liquid front that is progressively covering the area of wall that was previously exposed to the vapor in the interior of a bubble. So what happens? I have basically a hot spot that is covered by relatively fresh liquid. So there should be some heat transfer associated to this process. And that is precisely what both experiments and CFD simulations suggest. So you're beginning to understand why I was calling this a quench process. So here, these four images are actually from measurement, and we can see that actually as the bubble is beginning to depart, there is indeed some enhanced heat transfer in the where the advancing liquid front is present. So these rows of colored images here are a reconstruction of the heat flux at the solid from infrared camera images, and in the row below, these are the corresponding heat flux profiles along a line cutting through the measurement plane. And the interesting bit is that if we compare directly time after time the measurement of the heat flux and the heat flux from CFD simulation, which is done here in the images in the right, we get very good agreement. So we got the red line, that is the modeled heat flux from CFD simulation, directly extracted from CFD simulation. And the points with the black squares with the error band are measurements from direct measurements from observations of the bubble. So again, another example where we can see that the interface capturing approach is doing a good job at predicting the physics of boiling. So some other things of this kind are going on as part of my current research. And these are a number of fundamental studies of boiling going on right now at Manchester, and also with other co-workers at other institutions. So beginning from the left, there are some fundamental studies of flow boiling in small sized channels. So here the video, this grayish video has been obtained from X-ray measurements of a steam bubble growing and collapsing due to condensation in subcooled flow boiling conditions in a small diameter channel. And we are trying to reproduce this with interface capturing volume of fluid simulation. This is linked to activities in collaboration with industrial partner Rolls-Royce and in collaboration with Kyung-Hae University in Korea. Colleagues at Kyung-Hae are taking care of the experimental work, and we are doing the simulations in Manchester. Work on liquid films and microlayers is continuing. Again, simulations in Manchester, some experiments currently being developed at Imperial College. And at the same time, okay, maybe here I'm a little bit betraying myself, but there is also some work going on the macroscopic Eulerian modeling of boiling flows. At the beginning of my talk, I said that we wanted to move beyond it, when in reality, no, we're still doing some work on that as well, with codes such as ANSYS Fluent or Star System Plus, and this is part of a collaboration with the National Technical University of Athens. Now, for the time that I have left, I would like to linger on a little bit on these fundamental studies of boiling and give you an update on some of the interim results and results of validation and verification activities done to validate a methodology that we have recently published. So here I would like to show some results of the application of an interface capturing simulation techniques applicable to mass transfer that we have implemented using the open source library OpenFOAM. And these are verification cases in conditions, in experimental conditions taken from the literature for the case of isolated bubble growth. So bubble growing away from a wall in the presence of Earth gravity. So the bubble is also rising through the liquid, and so rising at the same time as it grows. And here from A, B, C, D, E, and F are 6 images at various time into the simulation of the growing bubble, where the color scale represents the temperature distribution around the bubble. And again, a good job done by interface capturing CFD at reproducing bubble growth. So here, okay, fine. I'm using in this plot on the right, I'm using log scale. So maybe, you know, the actual results don't look, are not as good as they look, but still in between the solid line that represents the equivalent bubble radius from CFD simulation and the various points that represent experimental results, there seems to be good agreement, provided that we're using very fine meshes, because here you can see we're using uniform meshes of size with cells of size of a few microns, whereas my bubble is something like 1 or 2 millimeters in radius. So here we're talking about very fine meshes compared to the bubble characteristic dimensions. So what do we want to do with this? Implementation with in OpenFOAM enables to solve the boiling equations and interface capturing model on arbitrary meshes that can be used to model boiling in complex geometries. And that's one of the goals of the research going on. And on the right here is an example of the things that one can do with this kind of methodology. These are actually images of bubble growth in pool boiling using the fluid properties of sodium, pool boiling from a cavity on a surface. So in the video, this isn't actually a case of gas injection from an orifice, but this is a bubble growing at a surface with particular features, in this case, a circular indentation, a cylindrical cavity. And in the video, the red phase is liquid sodium, the blue is its vapor, and these bubbles are growing due to the transport of heat from the surrounding liquid. So the methodology, in principle, to be demonstrated in the future, is capable of capturing the effect of surface features on boiling phenomena. A couple of things to conclude. Okay, fine. So what based on what we've seen, what can be the pros and cons of this methodology? Like I mentioned in my previous slide, so it is possible, and we have demonstrated that, to apply interface capturing methodology and to implement it in computational codes, in general computational procedures, such as, for example, that embodied in the OpenFOAM code, which enables simulation in realistic conditions using arbitrary meshes, and therefore enables to look at complex geometries with a relative ease of implementation in OpenFOAM. However, we have seen that very good mesh resolution is required in order to capture the behavior of these kinds of flows. So in the end, you need very fine meshes, which can be impractical if you want to run a lot of production runs for large-scale studies, such as, for example, parametric studies. So one possible way to come out of this impasse is to explore what may be a subgrid scale modeling approach to capturing interfacial dynamics, and therefore being able to use larger meshes to model the interfacial region, and basically not to spend so many cells for modeling, for example, one single bubble. However, having said that, there are also a lot of advantages associated to the use of interface capturing simulation, which is what, and I would like to conclude with listing some of these advantages, as well as showing some more videos of various examples of applications of interface capturing simulation, in this case, including also simulation setups where we have a small population of bubbles. So first of all, with interface capturing CFD and its application to boiling, we can capture the unsteady behavior of a fluid interface from first principles, so from via solving fundamental transport equations, and I have shown that we can directly extract quantities of interest from the simulation data, such as, for example, in that example of a bubble quench simulation. And thirdly, another thing that is promising is that the overall simulation methodology seems to be robust enough to be implemented using CFD framework, an already established CFD framework, such as, for example, that available for in the OpenFOAM CFD toolbox. And that's it from me. I would like to conclude with that. Just a couple of things, some acknowledgements. It's important, obviously, to acknowledge that at least some of the things that I have shown wouldn't have been possible without support from various institutions. So some of the work is linked to the activities of a research fellowship grant awarded to me by the UK Research Councils, by the EPSRC Council. And this is in parallel with a collaboration, with an industrial collaboration with the Rolls-Royce nuclear submarines. And in parallel, a couple of collaborations with colleagues from academia. So like I mentioned, for experimental validation, we are doing a lot of work with Kyung-Hae University, collaboration with Professor Hyung-Dae Kim. And some of the things that I have shown, in particular the quench bubble simulation, was done using a computational fluid dynamics code called PSI Boil, which is developed at the Paul Scherrer Institute in Switzerland in the group of Dr. Bojan Niceno. So been going on for almost 25 minutes. So that's it from me, really. Would like to thank you, but most importantly, would be happy to take any questions.
So there's one from Benedict Rajans in the chat.
Okay, so it depends. The answer to the question is, how long do my 3D simulations take? It depends. Actually, the things that I've shown today, let me see. I haven't shown very many 3D simulations. The Quench simulation was done in 3-dimensional configuration because the code works only in with rectangular meshes. So we had to do a quarter of a bubble, and that took a couple of days. That was rather short, but it really depends on the test case. And the multi-bubble simulations can take a few weeks in 3D configuration. Again, it depends, but it is not uncommon to have tens of millions of cells. So, question from Mariam: do you think adaptive mesh refinement could help with the problem of large number of cells? Yes and no, because things are a bit more subtle. So the point is that, I mean, if you think about the numbers, a CFD, even if it's a time-dependent CFD simulation, if you have, I don't know, 10 million, 20 million cells, they're not too many. You can, with a small, you can run on a small cluster, and that's it. The problem is that due to the modeling of surface tension in Navier-Stokes equations, so we have there is actually that poses a limit on how large your time step can be, both for stability and for accuracy. So even if you use very fine cells only at the interface, what counts is the smallest cell that you use. And therefore, you need to use very small time steps anyway, and you need to do many, many time steps. So at the end of the day, it's a trade-off. There is no silver lining. It isn't the case that adaptive mesh refinement is going to solve all your problems. Most likely, you will find yourself in a position where you need to wait for ages anyway for a simulation to finish, simply because the smaller, even if only a few cells at the interface are very small, that still forces you to use very small time steps. Which surface tension model am I using? I'm using the standard continuum surface force model. So the idea is that with that model, surface tension becomes a volume force located only at the interface cells. So the basic methodology is that of the continuum surface force model. Do you have parasitic velocities at the interface commonly seen with the CSF? They would be there, but we can kill them. We can kill them off in many ways. The way that I kill them off is I basically, so with the CSF model, continuum surface force, you compute the surface tension force from the interface curvature, and you compute the interface curvature from the gradients of the indicator function distribution around the interface. If you smooth the gradients, you can, and there are various techniques for doing so, you can reduce parasitic currents to the level where they basically do not disturb your flow anymore. It depends on how, on the importance of the surface tension force, obviously. If surface tension is huge, I don't think that smoothing will help you in the end. How do you define the thickness of the interface, and what is its effect on results? So there are many ways to define the thickness of the interface. Okay, so I can tell you what I do. That's basically related to the local characteristic dimension of the cells. And the idea is that you control the interface thickness with two terms in the equation that you solve for the indicator function distribution. So there is a compressive term and a diffusive term. They balance out at a thickness of the interface that is preset by the user. So you specify a little diffusion coefficient that tells you in the end how thick is going to be your interface. The effect on results is like the elephant in the room. Basically, if the interface is too thin, your simulation will be unstable. If it's too thick, well, no point using interface capturing, because it's, you will have your interface spread over many cells, so you lose a lot of detail. So it's a trade-off. But the approach that I'm using is established. So I mean, it's, we know its limitations, but for sensible values of the interface thickness, it works well.